that one can just take for granted. Okay, so that's pretty much the end of the introductory part, just to kind of give you a little bit of context for what we're doing and a little bit of motivation why we should do some of the things that we're going to do, and also some of the things that we're going to be looking out for, and some of the things that are very useful as cross-checks, because if you've done some calculations, some sanity checks are always useful. And one of the things you can realize here is that if you know something about the real emission calculation, you can check the infrared singularities over here. And conversely, if you know the infrared singularities over here, which, as it turns out, we also discussed in these lectures, you do on general ground, then you can check to make sure that you're assembling the real emission corrections correctly. These infrared singularities are dangerous, but if you treat them nicely, they become your friend. You can take advantage of them. So our goal is to learn or relearn how to do these tree-level and loop-level calculations. And that's what we're going to do using optional methods. Of course, for these simple processes, 2 to 2 or even 2 to 3, you can simply go ahead and use Feynman diagrams and pour them into a computer. When people had to do these by hand, they were very challenging calculations. But these days, you can just push a button. And I'm sure everyone has seen the CCG Feynman rules before. I'm not going to go through them in any detail, but just going to flash them on the transparency so that I can refer back to their structure a little bit later. I'm assuming everyone here has seen these before and studied these before. Is there someone who hasn't? That's a very embarrassing way to ask a question. Who has seen these before? All right, actually, look carefully. I think everyone has. All right. So there's, of course, a propagator dressed by colors. There's a 4-point vertex whose goal in life is basically just to restore. Over here. Now, for low-point functions, then we can certainly imagine just going ahead and calculating. The problem is, of course, we have to go out to, we're interested in going out to numbers of jets where you have 4, 5, 6 jets. And of course, we have 2 gluons in the initial state, so if we want to do 5-jet production, we're looking at a 7-point process. If we want to do 6-jet production, then we're looking at an 8-point process. And just to remind you or give you an idea of some of these numbers, then we can look at the number of Feynman graphs you would need to do. So if we're looking at, let's say, 2 to 6, then at tree level, it's something like 34,000 diagrams. Well, on a modern computer, it's not such a big deal. Of course, there's a lot of terms, and the 4-point vertices in particular produce a lot of them. And I think it's, we sort of get to something, I think, on the order of 25 million terms. Well, that's not such a big deal. If we go to 1 loop, then it's a little bit more serious because we're now looking at order 3 million diagrams, and that is going to produce order 20 billion terms. So it's times 10 to the 10th. And it's an amusing fact, but there's about 10 to the 11 neurons in your brain. So you would only have about 5 neurons for every term in this calculation. So it's not something that I think most people can do on the back of the envelope or certainly in their heads. Okay, well, some complicated calculation, you get some complicated answer, and the computer takes care of it. Who cares? The point, and we'll see examples of it already in this, of the tree level later on in this lecture, is that the answers are often very simple. There's a Spitzer theory to CCD, which some of you are actually working on, N equals 4 symmetric gauge theory, in which some of these answers, 2 to 6 or 2 to 9 or 2 to 10, you can write down on a single line. So if you have a calculation with 20 billion terms or 100 times that many terms, you get a single line answer, that's a sign you're doing something wrong. Because the quote I used attributed to Feynman, I don't know if it's actually said, you have a simple result, you have a simple derivation. And basically, the rest of these lectures are devoted to explaining to you how simple results, how a simple derivation, how that simple derivation gives you the tools to do much more complicated calculations. So the other point to make about these 25 million or 20 billion terms that are coming out of the Feynman diagrams, because the answers are very simple, it means that if you pick any single Feynman diagram out of these 3 million, then if you think about sort of an information theoretic point of view, there's almost no information in that diagram. That diagram is mostly noise. And that noise is coming because there's all this gauge variation and gauge variant states that are running around. So if we want to, and all this noise, of course, cancels at the end of the day, leaving us with a signal, which is the single line answer. So if we're good physicists, we want to filter out that noise as early as possible in the calculation. And to filter out that noise, we need to filter out all the gauge variation. And the way to go ahead and do it is to work as much as possible with on-shell quantities. On-shell quantities that don't have all this gauge redundancy built into them. Now, that doesn't mean that in some amplitude there's not effectively going to be lines off-shell. It doesn't mean that there's not going to be virtual particles circulating around the loop. There are. But we're going to learn everything about their contributions from objects where everything is on-shell, where all the gauge variation has been squeezed out. So we're sneaking up, in that sense, on the answer. And the things that we have to do in order to do these computations is to set up a certain amount of machinery. And I think most of that machinery Sir Paolo has already talked about this morning, so I'm just going to do a lightning review of it, actually just list the results on the board. And if I'm nitpicking and there's actually something he hasn't covered, then I'm sure he'll stop me. And we'll explain it some more. So the basic object, of course, that we're starting with, let's say we're looking first at tree level. And we've already seen that before we can talk about the next leading order corrections, before we can talk about the loop corrections, we need to understand the tree level corrections. And yes, it's true, there are technologies for doing this that are actually quite efficient, but it's very illuminating to understand how this works in an off-shell way. And in fact, in some respects, it also gives you some efficient representations for numerical use. So we start with an amplitude which, as we write it down, is a function of a triplet, a color index, polarization vector, and a momentum. And that object we can do a color decomposition. Again, the structure that I'm writing here is specific to all gluons, but there are analogous structures when we start to have form pairs. And of course, in n equals 4 supersymmetry, then the structure will be the same depending on whether it's gluinos or gluons. So we're going to have a sum over non-cyclic permutations. So Sn is the permutation group on n symbols. Zn is the cyclic rotation group. We're modding out by the cyclic rotations. We can decompose the amplitude in so-called color decomposition. And we have a so-called color factor times a tree-level color order amplitude. So in fact, this still has redundant information because we don't actually care about all the polarizations. We know that the quarks come two velocities. I'm sticking to math, of course, here for pedagogical purposes. The gluons also come with two physical velocities, and ultimately this function is a function only of those velocities, which is actually a 1 bit per external particle, and the momentum varies. The other ingredient, so this you saw this morning, right? The other thing that, the other sort of technical tool we need to introduce are spinor variables. And so we have complex two-component vectors, and we can write a momentum. We can knot the momentum into the Pauli matrices to obtain a 2x2 matrix representation, and that 2x2 matrix representation, we can write the outer product of two spinors, and the notation here is sort of following the supersymmetric kind of notation, A being A2 an object which is indexed from 1 to 2, and A dot an independent 1 to 2 index. And there are various notations that are used, so I'm going to probably favor the broad intent notation for the spinors, and we have plus and minus velocity, going to correspond to the ordinary and the tilde spinors. And of course we have the spinor product, which becomes the actual momentum, just writing the labels. And they come in two flavors, the angle bracket and the ordinary bracket. And the product of these things is precisely such that you get the momentum invariance. So each of these is complex, and if we're using real momenta, then their product is real. In fact, they're complex conjugates up to the size of the energy component of the momenta. So again, this is something we saw this morning. One other thing I want to emphasize or re-emphasize is that we can define an angle basically by, because the momentum is massless, an appropriate linear combination of the transverse components with some arbitrarily chosen z-axis. So k plus and k minus is the usual kind of right cone combinations. And with that, then we can write down an explicit numerical formula for signs right here. So we can write down an explicit formula for the spinor product, of course the equivalent one for the bracket product. And this is something that you can put on a computer, you can compute numerically. This is not just an abstract object that you manipulate analytically. Moreover, this is the efficient way of doing trace sums. There's a lot of calculations that you might be tempted to square and sum over ellipses analytically without a computer. Don't do that. Evaluate it using spinors at the amplitude level and square it numerically. It's much more efficient. If you have traces of gamma matrices that you have to evaluate, you might be tempted to use the formula that you find in the back of Peskin or your integral or whatever other field theory textbook you use. Don't do that. Do it this way. Right, so the one other bit of notation is that we can write this notation of the gamma matrix is really kind of a bastardized notation, and I will sometimes write it entirely without a sigma or a gamma faster. That's what these things all mean. Really, it is a sigma matrix inserted, and in fact, it's some more younger and more modern people also like to use a notation where there's no pluses and minuses at all, but where you just write the brackets and the angle, which means something like mu with an k minus, of course. If you have pluses, then you just split the brackets and the angle product. Is there anything here that you did not see this morning? Great. Okay, so the spinor product has a number of useful properties. And that, of course, immediately means that if you take the spinor product of some massless momentum of itself, you get zero. I realize that no one here is confused, but I'm going to say the following thing anyway, just in case. These are bosonic objects. There's nothing Grassmannian here. Minor signs do not come from Grassmann algebra. It's perfectly true that these arise most naturally. These spinors arise most naturally as wave functions for fermions, but they don't have to have anything to do with fermions, and this is a result of their structure, not a result of any Grassmann hiding anywhere. So there's a number of other identities. So, for example, we can reconstruct the momentum out of these spinors. Of course, that's just this equation written out in a different notation. And you've seen the Fear-Plate identity, I think, which is just the general, simple SU2 form of the general. So we sum over mu here, sum over sigma mu. And finally, there's the Houghton identity, which is just the fact that three in general, n plus 1 echelon tensors in n dimensions are not independent, and this is the two-dimensional version of that statement, such that we can rearrange spinors, and this, in practice, is the most useful identity for analytically simplifying expressions along with momentum conservation. And of course, there's similar identities for the bracket product. This is just the one for the angle product. We've also seen the spinor helicity representation, the so-called Chinese magic, which is due to Zhu Zhang and Chang in 1984, which is really a very elegant and covariant generalization of circular polarization. So this tells us basically how to put in an explicit representation that squeezes out the remaining information that is really not physical. So we have to introduce a reference momentum. And so the momentum of the gluon is K, and Q is a null momentum, but it's not collinear with the momentum of the gluon. And using it, we can write down a representation for the polarization vector, for the positive helicity and for the negative helicity. And you can easily check that it's transverse, the K dotted into this, either one of these two events. That should be completely obvious. The normalization is such that they're normalized properly, for circular polarization. Anyway, if you dot one into the other, then you get either 1 or minus 1. And I want you to observe one other thing. Of course, you can compute this by using the Sears identity. Note that if you dot, let's say, the positive helicity polarization vector into itself, you get 0. So, not really a requirement, but that's what happens, and I just want you to store that little fact in your mind somewhere. This Q doesn't, at this point in time, you can think of it as a real momentum. I mean, you'll notice that you're using both of the, that you're actually only using one of the spinors in each of the polarization vectors. And so that, for example, I mean, Cherpallo talked about this morning, when you do a phase rotation, then these transform by phase, and of course they transform by the same phase, so that the transformation of the reference moment doesn't affect your measurement of the helicity of either of these two vectors. So from that point of view, there's some decoupling between these, but I just think of it as a real vector. So you've seen that if I change Q for Q prime, that amounts to an on-shell gauge transformation. I'll pick up a term that's proportional to Ku, and of course that term, if I'm computing some on-shell quantity, will ultimately give 0. So that in some physical amplitude, it doesn't actually matter what Q I pick. As long as I pick something that's not collinear with K, I'll get the same answer. And I can pick Q in such a way as to maximize, if I'm still doing Feynman diagrams, maximize the cancellations. And of course, if you sum over helicities, you get a light cone projector. And there are a number of other simplifications that you've seen. I don't know if Cherpallo gave you any exercises or not, but here's one that I would suggest to exercise your understanding of the various simplifications and the various properties of the spinor helicity representation. So compute K4 with either 1 negative helicity or 2 negative adjacent helicities. And finally, this is sort of part A and B, and part C is compute the remaining helicity amplitude, but without doing any diagrams at all. So, you did this morning? All right, well, I guess you can't do it for yourself, but you should do it for yourself quietly anyway, not looking at your notes from this morning, just to make sure that you understood. I should mention that there is a Mathematica implementation, which has both analytic and numerical form, which is called SAM, and which in fact is due to Cherpallo and Daniel Meg. So I don't know if did you mention that? All right, so these things you modest. Okay, are there any questions about the spinor helicity representation? I haven't written down all the properties because I assume you have them in the notes from this morning. I just wanted to remind you of that. Here, up there. Okay, so let's do a little calculation. So, some of you may think that that 4-point object, those 4-point amplitudes are the simplest objects that we can calculate. But that's actually true. There's an even simpler object. And the simpler object that we can calculate, and we're going to calculate right now, is the 3-point amplitude. So we started with remember there's a cyclically symmetric version of the vertex. There's only one diagram to do, so that should be pretty simple. I should say I won't do it for you here, but it is possible to derive the form of this vertex just on general considerations of Poincare in there. So in fact, you don't really need a Lagrangian at all, but here I think it's nice maybe to see the connection to Lagrangian, so let's do it that way. So we're going to choose the same reference momentum for all light on Q, not one of these three momentum. And remember that we have the same helicity and the same reference momentum, then the dot product of polarization vectors and fashions. So there's actually only two terms that we have to compute. And that can avoid generating too much feedback from the microphone, then we'll actually manage to get through it. So we can use momentum conservation to rewrite the vertex in this form. I think the square root of 2 is probably missing in the Feynman diagram form, but it is actually there. So there's actually two terms that we need to compute. And let's just substitute in the spinor helicity representation, and then we're going to use the three-sided